Okay, let's dive in. We're looking at something out there in space, like a cosmic lighthouse, maybe, sending out pulses.
Right, but this lighthouse is acting, well, really strangely. It's pulsing incredibly slowly.
Almost impossibly slow, yeah. And the sources you sent suggest scientists think it might be something totally new.
Exactly. It's a real head-scratcher. So today, yeah, let's unpack the material you shared, try and figure out this cosmic mystery together.
Okay, so the object is ASKAP J1832 0911. Let's maybe just call it ASKAP J1832.
Yeah, much easier. And the first really weird thing, the thing that got it noticed, is the radio waves. It pulses, but only once every 44 minutes.
44 minutes. That's wild. Because typical pulsars, they flash multiple times a second, right?
Absolutely, per second. So 44 minutes is just, it's in a completely different league. That slow rhythm immediately flagged it back in 2022.
Part of this sort of new category, long period radio transients.
Precisely. A very small, very mysterious group. But ASKAP J1832 had another surprise waiting.
And this is where it gets really interesting based on the research.
This is the game changer. It's not just radio waves. Scientists pointed NASA's Chandra X-ray Observatory at it.
Oh, okay. Powerful stuff.
Very powerful. And they detected X-rays coming from it, too.
And that's a big deal because...
Because it's the first time, the very first time, X-rays have ever been found coming from one of these long-period radio transients.
Wow. So it's not just a radio thing scaled up. It's fundamentally different somehow.
It certainly suggests that, yeah. It adds a whole new layer to the puzzle.
And the timing of these X-rays...
Get this, they pulse on the exact same 44-minute cycle as the radio waves. Perfectly synchronized.
Okay, that can't be a coincidence.
No way.
Yeah.
And confirming that took some serious effort, combining data from different telescopes, Australia's ASKAP for the radio, Chandra for the X-rays, making sure they were coming from the exact same tiny point in space.
Right, and I saw they made those composite images, layering different types of light.
Yeah, X-ray, infrared from Spitzer, radio, seeing all those signals, all pulsed, all from the same spot that really pins it down to this one object. Different wavelengths tell you different things,
Like X-rays mean heat or magnetism, radio, maybe particle beams?
Something like that, yeah. So seeing them together, synchronized, it's crucial evidence.
Okay, so slow pulses, radio, and X-ray, same cycle. That's weird enough, but there was more.
There was another twist. Over about 6 months, the object's brightness, well, it faded dramatically.
Faded, like the pulses got weaker.
The overall emission, yeah. And crucially, it faded across both radio and X-ray wavelengths at the same time.
Huh. So you've got the short-term pulsing, 44 minutes, and this long-term fading over months. And that combination
is unlike anything we've ever seen before. Not in our galaxy, anyway. The research even shows these light curves, basically plots of brightness chopped into 44-minute bits, showing the pulse is steady even as the whole thing gets dimmer.
It really doesn't fit the standard playbook then.
Not at all. So naturally, the next question is, what is it?
Right. You start by ruling out the usual suspects. Standard pulsars.
Unlikely. The team looked closely at the signals, the intensity, the characteristics. Just doesn't match a typical pulsar. Or even a neutron star pulling stuff off a nearby star. The numbers don't add up.
Okay, so if it's not the common stuff, what are the sort of more exotic possibilities they explored?
Well, one idea is maybe it's a magnetar. That's a neutron star with a just insanely strong magnetic field.
Okay.
The thinking is maybe it's an old magnetar, perhaps over 500,000 years old. That might explain some things.
There's a catch, right? The research mentions a problem with that idea.
There is. It's the radio emission. For an old magnetar, the bright and variable radio signals we see from ASKAP J1832 are actually really hard to explain with our current models. It doesn't quite mesh.
Okay, so the old magnetar hypothesis is tricky. What's the other main possibility they looked at?
The alternative is a white dwarf, the remnant core of a star like our sun.
Yeah.
But not just any white dwarf. An isolated one wouldn't work. It would need to have a companion star, likely feeding it material.
Okay, a white dwarf binary system. That sounds a bit more plausible, maybe.
Well, here's where that idea gets extreme. For this scenario to produce these kinds of synchronized X-ray and radio pulses, the white dwarf would need to have the strongest magnetic field ever recorded for a white dwarf in our galaxy. Off the charts strong.
Whoa, so stronger than we even thought was possible for a white dwarf.
Pretty much. It pushes right up against, or maybe even breaks, our understanding of how magnetic fields work in white dwarfs.
Yeah.
It's a huge theoretical hurdle. It's not just tweaking a model. It's potentially needing a whole new one.
That is extreme. It makes sense why they mentioned it appears near a supernova remnant, though. That's where you'd expect neutron stars, magnetars.
It is nearby, yeah. But they looked very carefully at the distances and movements, and the conclusion is pretty clear. It's just a line-of-sight coincidence. They aren't actually related.
Ah, okay. And that actually pushed them away from only considering neutron stars.
Exactly. That lack of a real connection to the remnant made them think more seriously about other possibilities, like that supermagnetic white dwarf scenario.
So you've got an object. It pulses slowly in radio and X-rays. It fades weirdly. It's not a normal pulsar. It might be an old magnetar, but the radio is wrong. It might be a white dwarf, but it needs an impossibly strong magnetic field.
Right, when none of the existing boxes fit comfortably.
You start thinking maybe it's a whole new box, a new class of object.
That's exactly where the research points. It's such a unique combination of properties, and the known explanations require such, well, extreme conditions that the idea of a brand new class of cosmic object is definitely being considered.
Fascinating stuff. And this work was published in Nature, right? Led by Ziteng Wang.
That's right. And interestingly, another team actually found the radio source independently on the same day. Shows how much is still out there to find. And
we really have to credit the Chandra X-ray Observatory here. Without those X-ray detections, this would be a very different story.
Absolutely crucial. Chandra's been up there since '99, and it's just phenomenal at spotting these high-energy X-rays from the universe's hottest, most violent spots.
Like exploded stars, black holes.
And neutron stars, and potentially these very weird white dwarfs. Its precision has been key to so many discoveries over the years. It lets us see things totally invisible otherwise. Part of NASA's Great Observatories program for a reason.
Which really underlines why this deep dive, using the sources you provided, is so important. ASKAP J1832 isn't just some faint dot.
No, it's a challenge. It challenges our models of how stars live and die, how these dense remnants behave. It pushes the limits of what we thought white dwarfs or magnetars could even do.
And it really shows how vital it is to look at the universe with different kinds of eyes, right? Combining radio and X-ray here was the key.
Totally. Multi-wavelength astronomy often unlocks these brand new phenomena, things that force us to rethink everything.
Okay, so let's quickly recap this cosmic puzzle. ASKAP J1832 pulses radio waves super slowly every 44 minutes.
Check. Then uniquely, it also pulses X-rays on that exact same cycle.
Check. And mysteriously, its overall brightness faded significantly over just a few months in both radio and X-ray.
Double check. And it doesn't neatly fit any known category, not standard pulsars, maybe not even old magnetars or white dwarfs, without invoking truly extreme, never-to-foreseen properties.
Especially that first ever X-ray detection for this kind of slow radio object. That's the kicker.
Definitely a key piece of the puzzle.
So it leaves us thinking, doesn't it? If this one object, ASKAP J1832, defies our neat categories so much, if it forces us to consider brand new physics or even a whole new type of object, how much more weirdness is actually out there? How many other cosmic phenomena might exist that we just, haven't built the right tools to see yet, or maybe haven't even imagined the right questions to ask?